Hi everybody, my name is Gaspard Fougea. Just to give you a very quick background about myself, I studied mathematics. I then became fascinated by meditation. I studied meditation for 8 years. It's been fantastic. And then I've been wanting to combine mathematics and introspective study of consciousness. And I'm now doing a PhD on formal models for psychology. So for the next 20 minutes, I'm going to use the word psychology, but of course, consciousness theories are included in that. What we're doing here is we're leveraging the potential of theoretical computer science tools for the study of psychological phenomena and consciousness theories. So I'm a second year's PhD student. I'm going to show you a methodology that we've been developing and a tool for modeling on a theory of stress, the transactional theory of stress from Lazarus and Folkman, which is one of the most quoted books I think in the human sciences of humanities in the 20th century. It has more than 95,000 quotes. So here's the outline. We're going to ask why do we even talk about formal models for psychology? Then why finite automata? Why this specific tool? Don't worry if you don't have any background in theoretical computer science, I'll explain quickly what it is. We'll develop the transactional theory of stress. We'll show how to model it. And we'll talk about some mathematical transformations for theory building. So why in the first place do we need formal models for psychology, right? There is a crisis that's been expressed by some psychologists in the last 40 years. They say first that there's a lack of formalism in psychology. We have many verbal theories. What is a verbal theory? It's a theory expressed with words, with natural language. But as we all know, natural language is very ambiguous. A certain word can mean different things in different contexts, right? Whereas formal mathematical language is completely unambiguous. So the lack of formalism in psychology leads to less precision. This also leads to the difficulty to validate or falsify theories. It's more difficult to make prediction on something that hasn't the mathematical structure. There's also a lack of collaboration. So there's some papers who talk about this toothbrush effect, right? That between authors, the idea is someone else's theory is like someone else's toothbrush. I don't touch, right? I just use my own toothbrush. So it's a lack of collaboration. So there is this article from Robino and al. In 2021 that I'm going to read to you, which really captures all of this. We argue that formal theories provide this much needed set of tools, equipping researchers with tools for thinking, evaluating, explanation, enhancing measurement, informing theory development, and promoting the collaborative construction of psychological theories. So what we're trying to do with my PhD directors is offer one of these tools, a formal tool for theory building. And it's using finite automata. So why finite automata? So in psychology today, most of formal methods, of course there are many things, but most of them is statistics and probabilities. Now, when you read a psychological theory, take a look, next time try, very quickly you identify states and transitions. Like I'm in a certain mental state and something happens in that state, and then something happens and I arrive in another mental state, for instance. Well, that's the cool part. States and transitions are the key, the basic building foundations of theoretical computer science, of finite automata and all their extensions. You've probably heard of Turing machines, and then you can use tools of verification, logics, game theory. Basically, there's like 60 years of extensive research of how to study transition systems very formally, very precisely, and our hope is to leverage that power. So just to give you a very simple example, let's say that I define stress as when danger comes in, I'm stressed. When danger comes out, I'm not stressed. If a lion comes in right now, I go into stress. If the lion goes out, I'm not stressed anymore. Where here's a finite automaton representing that brilliant theory I just described, right? It's very simple. So this is a finite automaton, and you might wonder, okay, but what is a finite automaton? So I'm going to explain now. A finite automaton is a formal tool to describe transition systems, finite transition system. You have an alphabet, a set of states, transitions, and initial states. This is an example. This is my initial states. There's an arrow going to it. I start here. My system begins here. The arrows represent transitions. When there's an arrow from left to right, it means here with letter B, I can go from state Q1 to Q2. And yeah, and you have states, initial states. Yeah, I think I've explained everything. The alphabet is the letters we put on the transitions. So here's an example. I start in Q1. Okay, yeah, that's the formalism. Then I take transition B, and I arrive in Q2, right? You probably thought that would happen. And so you have a finite automaton, right, that can represent one module. When you have a psychological theory, you usually have many modules. There's memory, doing something here, over there, and then you have decision-making here, you have emotions there, and all of these modules may have independent behaviors, but may communicate as well. So here we use, again, a tool from theoretical computer science, which is synchronization and communication between modules, between automata. And here we use, I'm not going to go into the formal details, we use handshake synchronization, multiple handshake. Handshake means synchronizations happen at the same time, just like a handshake. You don't shake someone's hand 10 seconds after them, right? It doesn't make sense. Happens at the same time. So here is a system of 3 automata. See, 2 of them are very simple, just one state. The first one has 2 states. And this system can synchronize on letter B expressed here. Basically, set of automata can synchronize on one letter together. The only condition is that all the automata which have that letter in can take the transition. These are technical details. It's not so important for our purpose right now. So here's an example. Here are 2 automata, which are the automata we'll use later for the stress modeling. And the tokens are where we are in the state. So here we're on states NA and F. And then I take a toe transition. Toe transition just means I'm not explaining what happens. It's an internal transition. I keep it vague, and it's perfect for modeling because you don't want to explain everything at the same time. And you arrive in the state appraisal. Here, the 2 automata can synchronize on the stress transition, right? So we can take a transition together. Okay, and then we're back here. Okay, so we've done a bit of formal explanations. Now let's go back to psychology for a second. So the transactional theory of stress, as I said, it's still a widely studied theory. You still have so many papers coming out every year on this theory. It's quite wonderful, where it's originated in the 60s by Lazarus. So I'm going to explain to you some of the key components. We base ourselves on a 400 pages book, so it's just a little bit of it. So you have a person, right? No stress if there's no person. But one of the key points of that theory is stress isn't dependent just on the person and isn't dependent just on the environment. It's the relationship between the two that will create an evaluation in the person. The person with its parameters, the environment with its parameters. This evaluation, which they call appraisal, will give stress if there have 2 conditions. If right now I have a big lion roaring, entering the room, right? I'm going to ask myself 2 things. 1, am I in danger? Is it endangering my well-being? That's primary appraisal. And 2, what can I do? Can I hide? Can I run? Can I fight the lion? Right? And the answer to these 2 questions will determine my level and my quality of my stress reaction. Is this clear? Cool. So how do we model this? Let's take a look. And here, I'm going to go a little slow. You know, it's slightly technical, but I think we can do it. So we use, and that's what we're building. We're building, and we're still in progress, but we already have a methodology. We want to make it super formal, super mathematical, a methodology to take a verbal theory expressed with words from natural language. What do? You extract key concepts. So you start with the concepts that aren't defined by other concepts, right? You start with the axiomatic concepts, if you wish. You extract them, and you create an automaton. And then you use the mathematical tools called refinement, which I will explain later. And you successively point by point, step by step, refine and precise your model. This way of modeling is actually quite common in engineering and electrical modeling, etc. So that's a methodology to go from a verbal theory to a formal model. But replace that with any idea you have in your head with psychology, just any, or consciousness. You can apply the same method, and you can get a formal model that is both precise and also easily understandable by other people, because you've seen it's circles and arrows. Like, we can understand. It's, you know, it can take a bit of work. It's a bit technical, but it's more understandable than differential equations, for instance. Okay, so cognitive appraisal. Here's a sentence from the book. Cognitive appraisal is an evaluative process that determines why and to what extent a particular transaction or series of transactions between the person and the environment is stressful. Cool, so I want to model this. What do I think? Okay, there is a state in which I'm appraising. There may be a state where I'm not. You know what? Here it's a verbal theory. It doesn't say in that sentence. So I'm actually a bit free, but I'm going to decide there's a state where I'm not appraising. When I'm in the state appraising, there is a machine here which I haven't detailed at all that will tell me either I'm stressed or I'm not stressed, right? This simple system with two automata simply represents the idea that there is a state in which you appraise your environment. When you're in that state, you may receive the message that either you're stressed or you're not. Yes? Cool. I'm happy to take a little more time, but okay. So we add the environment, right? It's the transactional theory. You are looking at the relationship between the person and the environment. So what we do is we say, okay, let's just say it's an approximation, but the environment is a finite state system. Well, some people will say it's not an approximation, but that's a whole other debate. It's a finite state system, and when you're in a state here, double circles just means any state. We're not going to represent the gazillions of states of the environment. You can move with a transition that I do not precise. To means I don't explain, right? I'm not here to model statistical physics. I can move from one state to another. I don't really know how, and it doesn't matter. That's my environment. But regularly, I send a letter of my state to my appraisal automaton. And regularly, I tell him, hey, this is my state. The environment is updating the state to the appraisal automaton regularly. And in the appraisal automaton, nothing has changed. I've just reduced the letter stress to S and no stress to S bar, right? But it's exactly the same as up here. Regularly, I tell him, and he continues to say, while I'm in the appraisal state, I can say stress or no stress. Okay. So, hang on with me. It does look a little complicated, but I can explain to you the story behind it. I want to add these two questions, right? Remember, the lion enters the room. First question, am I in danger? Is there stress or not? Is there an issue here? Second question, what can I do about it? So, if in ANA, let's say I'm sleeping, I'm not appraising my environment, I arrive in PA, here, the lion enters the room, and I ask myself, am I stressed or not? It's still that machine that will tell me there, calculating stress. If I'm not stressed, I stay there. But if I realize, yes, the lion is actually a danger, it actually threatens my well-being, then there's this other automaton here where we move from just a neutral state to here. What do? This means that I'm choosing non-deterministically one action and I'm going to evaluate it. And I wonder if this action is good or bad. Let's say, for instance, the lion is in the room. Okay, what if I fight with him? What are my chances? And then I'm like, wait, no, that's not a good idea. He's going to eat me alive. So what other option do I have? Maybe I can run. And here, I can evaluate actions until finally I'm like, okay, this is a good action. Here is the cool part of our formalism, is once you've evaluated good action, we've just made the decision that once you think you have a good action, that's it, you act. This is coping. Coping, which has an effect here on the environment. But here, in this arrow, you can add literally any decision-making theory that you would like. And this is what I love about our tool, is it's collaborative. You can take a theory, you can add another theory to it, you can compare them. You can add the world, you can add inner representations of the world. It's very modular is the word I was looking for. So yeah, here are the modules you can add, and we have done this, we have tried it, it's doable. You can add a module that imagines a course of action and its results, a module that memorizes coping strategies, decision-making theories, that will calculate stress level. You can add a module that will, take a very close look at the phenomenal experience and wonder what consciousness actually is, just whatever you want. And this is a bit of a joke. Any compatible cognitive theory can be added here. So I've shown you a little bit how we've done it, but there are actually mathematical transformations there. And I'm going to show you quickly 2 of them. So refinement. What does it mean to refine? I have a system and I want to refine it. I want to make it more precise. Mathematically speaking, it means my system is more constrained. So here I showed 3 types of refinements. So S1 is one system where there are 2 automata, and S2 is another system where there are 3. And S2 is a refinement of S1. So for instance, in S1, the first state, we took a state and we split it in 2. In my first version of the theory, there was only 1 state. Now actually there's going to be 2 states. This is how we refine. Also in the second automata, there is a toe transition on the top. You guys see? Toe transition, remember, I'm not precising anything, which means I can say whatever I want. This transition was refined into a B transition, which is more precise, more constrained. The third type of refinement that I'm showing here is I added another automaton. For instance, I'm building my theory about consciousness or emotion, whatever. And then I want to add, I'm realizing that actually this has something to do with decision-making. I'm going to add a decision-making module here that I'm going to interact with. Adding another module is precising and refining my theory, just like it is to precise a transition or to split states in 2 or 3 or however many you want. This is my favorite. It's the merging. So what it is to merge, I'm taking 2 systems and I'm saying, okay, what happens if I actually merge them into 1? So if the 2 systems have no common states, I just put them next to one another, right? But then if they have common states, it's actually a bit of a more complicated situation. Well, there is a mathematical solution to it. You merge it, and then what happens? If your 2 systems represent correctly theories that are incompatible, you're going to end up with a system that doesn't make any sense, right? So we may have here a precise way of really seeing exactly where 2 theories aren't compatible. Precisely in which state, in which transition, in which mechanism does it not work. So this is why I really love it. It's still a work in progress. We already have some notions of it. It's not perfectly formal yet, but the idea is, I find, exciting. Okay, so yeah. Conclusion. We hope to really further develop the theory, have a very precise theory, to be able to have, to work with a psychologist who says, okay, I have so much data on this phenomenon, and I have an explanation for it. And we're like, okay, try to use our tool and create a formal model. And then they have a formal, precise model which can make predictions, which can help with theory building, which they can compare to another theory of the field, which maybe they can bring into an existing cognitive architecture. And we hope so to create the methodology, but also to create a library. So if we formalize in this way different theories, then we can put them together and maybe create some kind of cognitive architecture. And that's what I hope to do in the next 2 years.